Let's talk about graphing exponential functions, and let's talk about translations, reflections, all those kinds of things. I'm going to go through this fairly quickly. If you need to pause and rewind and watch the video again or go back and review something that I said, feel free to do that. But I'm going to go through this fairly quickly. The main thing that I want you to walk away from this quick review with is that exponential functions and logarithmic functions behave under reflections and translations exactly like all other functions. We've already seen the parent functions when we went through those videos not too long ago, and we know that this is true. But I want to cover these a little more in depth, and I want you to see that this is the same for any other parent function. First of all, let's talk about an exponential function with base b raised to the power of x. B is the base. And we know some things about the graph of our exponential function based on the value of our base. When our base is greater than 1, our function will be everywhere increasing. That's the red graph that's on the page in front of you. When our base is fractional, or between the values of 0 and 1, our graph will be everywhere decreasing. We know both of those cases we have a horizontal asymptote at y equals 0 or along the x-axis. It is also true, even though it's not here, that b cannot be a negative real number. B must be a positive real number other than 0 and other than 1. In those cases, we will get a graph of one of these two types depending on which interval your base falls into, between 0 and 1 or greater than 1. We've already discussed this at length. Exponential functions and logarithmic functions are inverses of one another. Exponential functions do not have x-intercepts or roots or zeros. Logarithmic functions do. Exponential functions have a horizontal asymptote that is the x-axis if they haven't been translated or reflected. Logarithmic functions have a vertical asymptote that is the y-axis, again, if they haven't undergone any translation or reflection. We know the logarithmic function is decreasing if the base is between 0 and 1 and increasing if the base is greater than 1. We know that they are a set of inverse functions. We know analytically inverse functions undo each other's operations. We know graphically those functions will be mirror images, reflections of one another over the line y equals x in the plane. If you have that situation, those two functions are inverses of one another. If that's the case, the domain of one of those functions will be the range of the other function. And the domain of the other function will be the range of the first function. Those two things are reversed. We discussed that already in depth, so I'm not going to spend a lot of time. This was when the base is greater than 1. That's what the graphs look like. Here's what the corresponding graphs look like when the base is a fraction between 0 and 1. They are still inverses of one another. Here is a set of inverse functions. These two functions are very important to us in calculus. You will use them so much you will become very comfortable with them. They are a set of inverse functions. They undo one another. Everything that we said was true about a log to base a is true about this logarithm. Its base is just e. We talk about the value of e. It turns out that we have an expression of 1 plus 1 over n to the n. As input values of n get really, really, really big, and you can see here we're up to 1,000,000. The corresponding output values, there's n values, there's output values. The corresponding output values as n gets bigger and bigger and bigger and bigger settle really close to a value of 2.718281. E is a value that can be expressed by a non-repeating, non-ending decimal. But I want you to understand E is exactly E. This is an approximation. This approximation has error. This value, no error. So we're going to be using E a lot. It is a real number value, just like pi. 3.14 is an approximation of pi. This has error. This does not. That is exact. Pi has a value of pi, not a value of 3.14. Pi has a value that is close to 3.14. I want you to think of E in the same way. E has a value that is just slightly less than 3, specifically 2.718. But it has a value of E. So get comfortable using E as the base of an exponential function. Here are the graphs of 3 exponential functions. Y equals 2 to the x, y equals 3 to the x, y equals e to the x. Notice that the graph lies in the plane below y equals 3 to the x. Here's why. Remember, E is really close to a value of 3. If you're doing something with E mathematically, and you're just not comfortable with it yet, pick up 3 and do the mathematical operation with 3. E is going to act a whole lot like, under analytics, a whole lot like 3 will. So practice with 3 for a little bit, and you'll get comfortable substituting E in there, and you know that's how it will behave. So just like we talked about in translations of parent functions, these exponential functions are going to behave in the same way. If we take our entire function, parent function, and we add or subtract a value outside of the operation on that independent variable, that is a vertical translation, just like it was for all other functions. When C is positive, it is a vertical translation up. When C is negative, it is a vertical translation down. Exactly like what happened with our other parent functions. When we have a parent function where the independent variable inside of the operation, this is inside of the operation that raises some input value and makes it the exponent to the base of b. When we are inside the operation, next to the independent variable, remember that was a horizontal translation. Just as the other functions, if what you see is a plus c, because what's actually happening there is a minus negative c, it is a movement horizontally in the plane to the left. If what you see is a minus c, it is a movement horizontally in the plane to the right. Exactly like what we discovered about our other functions. When we have a function and we put a negative out in front of the whole function, we said everything that was positive outputs has now become negative outputs. It is, as with the other functions, a reflection over the x-axis. When we take that function and we put the negative inside the operation, everything that was a positive input value is now a negative input value, and everything that was negative now becomes positive. In effect, just like the other functions, that is going to evidence itself by a reflection over the y-axis. So these exponential functions act exactly the same as all the other parent functions that we saw. Stretching and compressing. When we put a real number value in front of our function operation, here we're calling it c. If c is greater than 1, that is going to stretch the outputs of our graph. If c is a fraction or less than 1, that is going to compress or shrink the outputs of our graph. If we put c inside of the function operation next to the independent variable, we are cycling through our x values faster if c is greater than 1. So we're going to actually compress or shrink horizontally the graph of our function. If c is less than 1, between 0 and 1 specifically, then we're not going to go through those horizontal values as quickly as the original parent function. So it's going to look like a stretching of the graph horizontally. So everything that we talked about when we talked about stretching, compressing, reflecting, translating, everything we talked about on our parent functions is still true here for exponential functions. Everything that we learned about where our constants wind up, where our negatives are, whether they're inside next to the independent variable or out front and only affect the dependent variable, all of those things are still true. So come to class next time, we'll work some homework problems.